Last time, we explored 3D geometry and the introduction of cross-sections, techniques that allow 3D geometry problems to become 2D geometry problems. This time, we're taking it one step further, and we're going to look at some more tricky cross-section problems. Starting off over here, a sphere with center O has radius 6. A triangle with sides of length 15, 15, and 24 is situated in space so that each of its sides are tangent to the sphere. What is the distance between O and the plane determined by the triangle? So just to make it clear here, this thingy is flat. This triangle is flat. So you imagine a sphere. This triangle is kind of wrapping around the sphere. It's not going from the bottom to the top, as it might look like in this diagram. We have this flat triangle. So what cross section do we want to take? Well, naturally, we've got a triangle, and that's kind of like the central focus of this problem. So it makes sense to take the cross section through the triangle. What happens when we get that? So let's draw our triangle here. We know it's 15, 15, 24. That's helpful, right? 15, 15, 24. That's really, we want to try and use that information somehow. We don't know how yet. This is our triangle, and what is this at the center of the triangle? Well, it's of course going to be a circle. So we have a circle here. Is this going to be the radius of, is this going to have the same radius as the sphere's radius? No. This would have a radius of 6 if the center of the sphere lied in the same plane. So if this point over here, this point in the same plane as the triangle was the center of the sphere, then yes, this would have a radius of 6. Because the radius of a sphere is the distance between the center and any other point. But the center of this circle is a point above, it's a point you can imagine at the center over here. It's above the center of the sphere. It's not the center of the sphere, however. So we know this is going to have some other radius r that's going to be less than the radius of the sphere because it's above it. This circle over here, let's actually draw out what this circle would be just to make it clear. It's going to look, in this 2D diagram, it's going to look more like an ellipse than a circle. But in reality, if you stretch it out, it's going to be a circle. Something like that is how it will look like in our 2D diagram. But of course, like I said, it's the same as this circle over here. So the radius of this is also r. But then if you have the center of the sphere over here, let's draw the center. This is 6. And really, what is it asking? It's asking for the distance between O and the plane determined by the triangle. So this plane, really. And it can be a little bit counterintuitive if you're new to 3D Geo, but these two lines, if you connect O to the center of this orange circle, connect that, let's draw that line, it's going to form a right triangle. Now you might be like, that doesn't look right at all. And that's the thing about this. Because it's a 2D drawing, it requires visualization. If you imagine a plane, imagine this in 3D, and imagine this is our plane with a triangle, including the smaller circle. And then this is the center of the circle. That's going to be perpendicular. And of course, when you do a 3D model, it's not going to look so much perpendicular anymore. So this is perpendicular. What are we trying to find? The distance between O and the plane determined by the triangle. So we're really just trying to find the length of this pink segment. We've got 6, and we've got a right triangle. Pythagorean theorem. All we have to do is find this r, which is the same as this r. But that's the in radius of this circle. So now all we have to do is find the in radius of this triangle, and then we can use Pythagorean theorem to solve for that. So what's the in radius of this triangle? Well, if you've watched the previous 2D videos, this is easy for you. Area over savvy perimeter. Area, well, you can use herons, but there's a slicker way to do this. because it's isosceles triangle, can drop the altitude, 12, and then 9, 12, 15, Pythag triple. So now the area is two triangles, times 1/2, 9, 12. And this is 2 times 54, which is 108. So the area of this triangle is 108. The semi-perimeter is 15 plus 24, all divided by 2. And 15 plus 15 plus 24 is 54, divided by 2, 27. So our in radius is 4. So this r is really just 4. And now we just use Pythag theorem. We have the distance squared plus 4 squared. Let's do it somewhere else. We have distance squared plus 4 squared equals 6 squared. And then distance squared is then 36 minus 16, 20. And therefore our distance is just 2 root 5. And that is our final answer for this problem. 2 root 5. So the key idea here, really taking the cross section of this triangle, because then that gave us a circle in the center here. This circle has a radius that's of course not going to be the same as the radius of the sphere. What we did now and realize is the distance of the plane, 6, and this radius, they form a right triangle. So we know the radius of the sphere, and if you can find the radius of the circle, we use Pythag to finish. But then the radius of this circle was just the in radius of this triangle, and that's all we needed to solve this problem. Okay, now let's take a look at a more tricky example. This one is from the AMC 10. Inside a right circular cone with base radius 5 and a height of 12 are 3 congruent spheres with radius r. Something like that. Oops. Okay, so let's try and visualize what these 3 spheres will look like. We've got 2 like that. Let's see. Make this bigger here. So each of the spheres is tangent to the other 2 spheres, but they're also tangent to the base and side of the cone. So they're tangent to each other, and they're also tangent to basically everywhere in the cone. I've drawn 2 spheres here, and you can imagine a third sphere would be something like that. I'm not going to draw it, but you can imagine it's behind these 2 spheres. Right now, we're basically looking at the front view. So we're basically asked to find the radius of each of these 3 spheres. They're all congruent inside a right circular cone, which we know the dimensions of. This is 5, and the height is 12. That height is 12. Okay. So what cross section do we want to take here? That's the key thing here. We've seen many problems. When you have a bunch of spheres, it's a really good idea to take a cross section of the plane through the centers of those spheres. Because, then we have a bunch of circles in our 2D problem. So let's do that here. Naturally, that's the most logical thing we can do. So let's draw what plane we're really taking the cross section of. Let's get a highlighter for this. So we've got this thing right over here, just like that. And imagine that plane with the 3 centers. Now imagine we unfold it out onto a 2D plane, like that. What do we get? We get a bunch of circles. So we get 3 circles, all of which are tangent to each other. And in addition, they're also tangent to the cone. Or the spheres are tangent to the cone. But the question really is it tangent to this outer circle? And it would be a very common mistake to say, yes, of course, it's tangent to the cone, so it should also be tangent to this orange circle. But that's where many people actually got tripped up on this here. The key thing was that, let's erase this orange thing here now. Let's draw the radii in. R, R. Notice how in this cross-section thing, these circles are actually not touching because they're tangent at a point that's above. So we have to be very careful here because we can't assume, it's a wrong assumption to assume that they're going to be tangent to the orange circle. So now let's label our radii in this 2D model we have here. R, 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 R. So the thing is here is, if it's not tangent, what do we really do? I mean, these things, this distance is not 0. But is there any way maybe you can still find what this distance is? If it's not 0, maybe it's something we can find. So really, let's draw in 2 places. One in our 3D diagram and 2 in our 2D cross section, so we can get a good understanding. We have this distance here, and we have this distance here. Those are the same thing. So let's try and find this distance here. So of course we've got tangency, so 90 degrees. So this distance here, it seems like if we can find the ratios in this triangle, then we could find this green distance. Ratios in this triangle, similar triangles maybe, and are there any similar triangles here? Let's see, this angle, or let's talk about the other angle. This angle is equal to this angle by parallel lines, corresponding angles. Aha! This is also 90. So this triangle and this triangle, they share 2 angles. The right angle and the 90-degree angle. Therefore, they're similar. And that means that the ratio of this leg to this leg is 5 to 12. And by Pythagorean theorem, we would also have that the ratio, since the ratio of this to this is 5 to 12, the ratio of this to this is 12 to 13, because 5, 12, 13 triangle. So this distance over here would be 5 twelfths r, and then this green distance would be 13 twelfths r. Let's mark that here. That's pretty useful, right? And that really tells us is that this part extra is 1/12 r. That's really useful. Okay, so now how do we find the radius? Well, first of all, we have this equilateral triangle here, and that's useful. So let's look at the center of this orange circle, this highlighted orange circle. We have this distance and we have this distance. What is this distance over here? We've got an equilateral triangle with, well, we can just drop in altitude and use 30, 60, 90s. Let's drop in altitude. This is r. This is r over root 3, 30, 60, 90s. This is 2r over root 3, again, 30, 60, 90s. So in total, the radius of this orange circle is 2r over root 3 plus 13 over 12r. But remember that this radius of this orange circle is the same as this distance over here, because the orange circle we're talking about is just this circle here. So this distance from here to here is also the radius of that orange circle. How can we possibly find that distance? We can use similar triangles yet again. So notice that these sides are parallel. We've got another pair of similar triangles. Aha! So now let's just write our similarity equation. So we have this, which is what we're trying to find. Let's call it x. X over whatever this distance is. What is this distance? This whole thing is 12, and this part is r. So x 12 minus r is the same as 5 to 12. And solving for this, we just get x is just this quantity here. 5 12s times 12 minus r. But x is also equal to this, 2r over root 3 plus 13 over 12r. Right? Remember, we found this was 2r over root 3, and this was 13 over 12r. And this was x, or what we called x. And now we have an equation in terms of r. So now we can just solve for r. It's just that simple from here. And this is a one variable equation. That's all we have left to do. 5 minus 5 12ths r. And then we have equals this, 2r over root 3 plus 13 over 12r. Okay, so let's add 5 12ths r to both sides. And this gives us 2r over root 3 plus 3 halves r. This is 5. So r is just 5 over 2 over root 3 plus 3 halves. And we multiply by 2 root 3 to the numerator. Multiply by 2 root 3 to the denominator. We get 10 root 3 over, and then 2 root 3 here, we get 4 plus 3 root 3. Just by multiplication. And now we rationalize, so 4 minus 3 root 3 over 4 minus 3 root 3, or maybe it would be reverse actually. Because then 3 root 3 minus 4 is positive, so you can reverse that. And then now this is just difference of squares, so that we got 11 in the denominator. And then in the numerator, we have 90 minus 40 root 3. So that is our answer, 90 minus 40 root 3 by 11. Not the nicest looking answer, but still a really great problem. The key thing was, look at the cross section of this plane of the three centers. And then once we had that, remember, circles are not tangent. The tangency point is above. But that didn't stop us, did it? We found this distance. We found this distance. We basically found this distance in two different ways. One, using our cross section, 2 over root 3r plus 13 over 12r, which remember we found by our similar triangles. And we also found it using our original triangle over here, which is kind of like another cross section of its own, kind of. So that was, we found this distance over this distance equals this over this, similar triangles, one variable equation, and boom, solved. Cool. Let's check out another example. A 4 by 4 by 8 rectangular box contains a sphere of radius 2 and 8 smaller spheres of radius 1. Smaller spheres are each tangent to 3 sides of the box. The larger sphere is tangent to each of the smaller spheres. What is the height? So many spheres here. 9 spheres. That's a lot to deal with. It's very tricky, to deal with the 3D geometry problem, just working it, trying to visualize everything in 3D. Let's take a 2D cross-section. We have to learn to take the right cross-section, right? Because taking a cross-section like this, for example, won't really do anything. We'll just get a circle in a square. That's not a very useful looking cross-section. It doesn't give us any information about what the height will be, really. So let's just take a look at the centers of these circles. That's kind of been a theme here in these 3D Geo videos. Looking at the centers of all of these circles and generally looking at cross sections through them. I've labeled all the centers. So the key thing we want to find the height. We want to find some expressions in terms of the height. Is there any distance we can somehow get that's in the vertical direction at least? We're not going to get the height directly just by adding 1 plus 2 plus 2. That's not going to work. But maybe we can get some other quantity by connecting radii. Because just like how if you have two circles in the 2D plane, and like this is, let's say, 1 and then this is 2. The distance between these two centers is 3. The radius of the first circle is 2 and the second circle is 1. It's something very similar is true in 3D. So we have, let's draw it here. This sphere has a radius of 1 and this one radius of 2. The distance between these two centers is 3. Wait, but then by symmetry, take a look at this back sphere, like this one here. Imagine you go into the page, that sphere. That's also going to have a total distance of 3. So in total, this is a straight line. Hopefully I draw it a little bit better. So imagine this is the center of the middle sphere. We have that this distance is 3, and this distance is also 3. In total, the distance between these 2 points is 6. Okay, so here's where we're going to try and take a cross-section, because dealing with this weird diagonal length, well, if you're good at 3D Geo, you won't really need to take a cross-section, but a cross-section is sometimes an easier tool to help visualize and figure out what's going on. So we can have a rectangle. And what we just found, what is this rectangle I'm drawing? So the key thing is, let's take the cross-section of the plane through the centers of this sphere, this one, and this one. So let's draw what that really looks like. We've got this here. We've got something like this. I think I drew that a little bit inaccurate, or something like that, yeah. And then, yeah, let's see. What's the best way to draw this? Connect this. And something like that. No, this is not a good... So, you can imagine you connect all of these spheres. This one, and then this one as well. The one that goes back like this. Okay, I misdrew the thingy there. So the center of the back sphere is like that. So we have something like this. That green dot, the big one, represents the center of that sphere. So this is really the plane. This green rhombus kind of thing is a plane we're looking at. The center of this back sphere, the center of this front sphere, this center of this sphere, and the center of that sphere. That plane, if we kind of unravel it, we can see that this dimension is 2. Because 1 plus 1. The two centers, there's 2 spheres. They both have radius 1. So the distance between them is 2. That's what this is, 2. And then now we know the diagonal of this rectangle. We know this length. We found that to be 3 plus 3, if you remember from earlier. 6. And, probably you already recognized it, Pythagorean theorem. Call this x. X squared plus 2 squared is 6 squared. So x squared is 36 minus 4, 32. X is 4 root 2. So now we found x, which is this. Let's draw it in a thicker color. This is x, this distance. And we know that to be 4 root 2 by Pythagorean theorem. But that's not even the height. Now what are we going to do? Are we stuck? No, because what we're going to do is take yet another cross section. Or if you probably don't need to, but just for the sake of demonstration, let's take the cross section of the plane through the centers of these 4 spheres. I'm going to do that on the side over here. Okay, let's see. We have this diagonal is 4 root 2. And just like earlier, the distance between these two spheres, 1 plus 1 equals 2. Again, Pythagorean theorem. Let's call this distance y. We have y squared plus 2 squared is 4 root 2 squared, 32. So y squared is 28. Y 2 root 7. So what was y? Y was this distance here, which is resemblant of this distance here. From top to bottom. The height is just going to be y plus this top radii and this bottom radii. This was y. And we're adding on to that 1 and 1, a total of 2. So our answer is just 2 plus 2 root 7. And that's it. We're done. Let's quickly recap the main steps. The first thing to realize was that this whole tangency thing, we want to draw the radii. We have 1, 2, 2, and then back there 1 again. So we use that 6, as well as this distance 2. We used all of that stuff, and we used Pythagorean theorem, and we found the value of x, which was this distance here, 4 root 2 we found it to be. And then we found let this distance be y, and using Pythagorean theorem again, we found the value of this distance here. 2, 4 root 2, we can find this, which is almost the height, but there's 2 extra little ones here. So then our answer is just 2 plus 2 root 2, and we are done. Be sure to check out the next video where we talk about area and length of complex shapes. Some cool looking figures, some funky looking ones, and we're going to tackle them in the next video. You can click on that one right there.